Welcome back to Applied Mathematics. In this video, I want to introduce you to systems of equations. A system of equations is a collection of two or more different equations which provide different sorts of constraints on the same problem. We're going to, in this lesson, specifically be looking at systems of two linear equations in two variables. So let me get my head out of the way and let's just start writing. A system of two linear equations in two variables is any system that can be written as sum a times x plus b times y equals c, and then d times x plus e times y equals f. In this notation, x and y are our unknowns. A, b, c, d, e, and f are the parameters that are given to us, or in more practical applications, they're the things that we have the information to figure out directly. A solution is any ordered pair xy that satisfies both of the equations in the system. And again, that's a definition that can be extended. If you have a system of 3 or 4 or 27 different equations, then the solution has to satisfy all 3 or 4 or 27 equations. If you have an equation in 3 or 9 or 17 variables, then instead of being an ordered pair, it's going to be an ordered triple, or an ordered 9 tuple, or an ordered 17 tuple. It will have however many pieces of information as you have equations. But we'll stick with the simple example for now because it makes life a little bit easier. There is a result in linear algebra that says that the only time a system of equations has a unique solution is when the number of equations is equal to the number of unknowns. There's a lot of fuzziness in that. It turns out that it's actually pretty easy to write a system of equations in this form that still does not have a unique solution. But it is impossible, well, mostly impossible. Okay, it's somewhat difficult to write an equation that does not have this setup and still has a unique solution. We call a system overdetermined if it has too many equations and you can't satisfy all of them. There is no solution in this case. An overdetermined system has equations that contradict each other. It is impossible to satisfy this equation and that equation, or these two equations and those two equations at the same time. An underdetermined system is just the opposite. There's not enough information, and so you still have infinitely many different possible solutions. These are things that can and will come up. But let's jump in and start looking at an actual example. Here I have 2x minus 5y equals 1 and 4x minus 3y equals 9. I can start by looking at each of these equations individually. Each is an equation in two variables. It is a linear equation, so I know how to graph it. I could do the graphing by hand, or I can turn to Desmos and let it do the work for me. I have these two equations graphed, and now, if you remember that the graph of an equation is the collection of all of the points that satisfy that equation, well then, the point that satisfies both of the equations is the point where the two lines intersect each other. It really looks at a glance that that's going to be at the point 3, 1. Desmos will actually take things a step further and do even that for us. If I go to one of these equations just to highlight it, you'll see a couple of points get indicated as points of interest, including the point where the two lines intersect. If I click on that point, it will tell me that that point is 3, 1. I can hit this export point, and that will put it over here on my list, and it won't go away. I can keep it forever. I can print out the graph with that point displayed. Okay, that's it. We're done. Computer can do it for us. There's a couple of things that need to be kept under consideration. First one, the practical choice. During exams in this course, you will not be able to use Desmos to do the solving for you, so you had better be able to do it for completing the exams. That is a terrible, threatening way of giving you motivation, but it does exist. There are a couple of other things that come up as well. It turns out that for solving more complicated systems, Desmos is not going to be of any help anymore. As soon as we get away from systems in two variables, Desmos cannot help us. There are other tools that will help in certain circumstances. And some of those tools are great, and some of those tools are a little bit cumbersome. I would never try to solve a system in 7 variables by hand. But when it comes to a system in 3 variables, that's where I'm starting to be tempted. The amount of time that it takes to set up the computer to solve the system for us rivals the amount of time it takes to solve it by hand. So there is a cost-benefit analysis to be done between the two. You can't do that analysis unless you have the basic tools, and the best way of developing those basic tools is to practice on the easy ones. So let's go to our notes and let's look at this same system of equations, and let's see if we can figure out how to solve it. There are a couple of different tools at our disposal for solving a system of equations. The first one I want to show you is called the method of substitution. The method of substitution asks us to take one of the equations and rearrange to solve for one of the variables. It doesn't matter which equation, it doesn't matter which variable. I'll take the first equation and solve for x. Now that I have this expression for x, I'm going to take that and substitute it in where you see x in the second equation. So we have 4 times x, but x is 5y plus 1 over 2. That's where the name comes from. We substitute an expression for one variable. Now we have a kind of ugly expression, but it only has y in it. And because it only has y in it, we know we will be able to solve it. Right? 4 divided by 2 is 2. I can distribute, combine some like terms, and then subtract 2 from both sides of the equation, and divide by 7 to get me y equals 1. That's half of the battle. I'm now going to take that y equals 1 and plug it into the expression that we just came up with for x. X equals 5 times y, but y is 1 plus 1 over 2. And that gives me that x is equal to 3. Finally, I will write my solution as an ordered pair. The x-coordinate is 3, the y-coordinate is 1. My solution here is the ordered pair 3, 1. That was a long way to go to get exactly the same solution we had come up with in Desmos, but that's very typical of mathematics. We'll start with the easy problem, and we'll make it a lot harder than it needs to, so that when we get to the harder problem, it will be a little bit easier. Let's take a look at one other example. (3x minus 5y equals 2) and y equals 3/5 x plus 4. When it comes to the method of substitution, this one is very exciting because half of the work has already been done for us. We already have that second equation solved for y, so we can just immediately plug it into the first equation. And then start going from there. Distribute. So we have 3x minus 5 times 3/5 is 3 times x, and then minus 5 times 4 is minus 20, and then combine some like terms. 3x minus 3x is 0x, or just 0, and we get that negative 20 equals 2. Well, there's a problem. Negative 20 is definitely not equal to 2. This equation is false. We've said nothing about the value of the variable. We've gotten out that the equation is false. That tells us that there is no solution. Or, as we had described it, this is an overdetermined system. I'm kind of curious to explore that a little bit further, so let's jump over to Desmos and type in these two equations. We had 3x minus 5y equals 2, and we had y equals 3/5 x plus 4. And when you look at the graph, those are two parallel lines. Parallel lines are defined by the behavior of never intersecting each other. If you have two lines that never intersect, there is never going to be a point on both of the lines. That's the definition of intersect. And so that's what we mean when we say there is no solution. This line and that line can never both be satisfied at the same time. You have to choose one or the other. There are too many constraints on the system, and there is no solution. So algebraically, this is one way that no solution can show up, and we've seen what that looks like as far as trying to solve the equation. We end up in that situation that has no solution. I think that's enough to talk about here. We will build on this. We'll look at the other method for solving a system, the method of elimination, a little bit later. We'll build this out and we'll look at systems involving 3 or more equations, and we'll look at some of the more sophisticated numerical tools in future videos. But for right now, I'm going to wrap up with that, so thanks as always for joining me, and I'll see you next time.